Welcome to This Explainer. Today we're diving straight into the invisible muscles powering heavy machinery. We're going to unpack a pretty fascinating and highly structured document, the Certified Rwandan TVET Board Training Manual for Manufacturing Technology. Specifically, we're looking at the RQF Level 5 module that covers the basics of hydraulic and pneumatic systems. If you've ever wondered how our modern infrastructure is actually built and maintained, well, you are definitely in the right place. Let's get right into it. So, let me ask you a question to kick things off here. How exactly do modern machines manage to move literal mountains? Seriously, think about it. When you see those massive excavators lifting tons of earth, or factory presses shaping solid steel like it's just warm butter, where does all that immense, concentrated force actually come from? Well, it's not just gears and electric motors. The real secret lies in something much, much more fluid. And this brilliantly illustrates the answer. Whether you're looking at a simple, everyday hydraulic jack that can lift a heavy car with just a few pumps, or a massive, complex network of industrial pipes in a factory, the underlying principle is exactly the same. It all boils down to the sheer, contained physical power of fluid mechanics. By manipulating fluids inside confined spaces, we're able to generate absolutely incredible physical power. Now, before we get into the gears, or, well, actually the valves of how all this works, we need to credit the official sources for this knowledge. Everything in this explainer is drawn directly from a rigorous Level 5 RQF module, developed by the Rwanda TVET Board, which had technical and financial support from KOIC, that's the Korea International Cooperation Agency. You know, this isn't just theory we're talking about. This is the certified foundational training that guarantees the safety and reliability of the technicians out there building our world. Okay, so here's our roadmap for today. First, we'll cover principles and core components. Second, designing system circuits. And third, building and testing systems.
All right, let's jump straight into Section 1, Principles and Core Components, the basics.
So the really crucial point to grasp here is that both hydraulics and pneumatics are essentially the circulatory systems of modern machinery. They aren't relying on belts or chains to move energy from a motor over to a mechanical arm. Instead, they use fluid mechanics to transmit that raw power. And whether that fluid is a liquid or a compressed gas, the ultimate goal is exactly the same: to generate, control, and expertly transmit power precisely where it needs to go in a manufacturing environment. So what's the actual difference between the two? Well, hydraulics relies on incompressible liquids, usually specialized oils, which allows them to transmit massive amounts of force incredibly smoothly. Technicians measure the thickness of this fluid, its dynamic viscosity, using a unit called centipoise. Just think about the difference between pumping water versus pumping thick honey. Pneumatics, on the flip side, uses highly compressible gases, like regular air. Because air acts kind of like a natural spring, pneumatic systems are often much faster, cleaner, and absolutely perfect for those rapid, repetitive motions you see on a factory assembly line. Now, to actually harness all of this fluid power, you need some very specific components. Think of these as the organs of the machinery. First up, you have the FRL unit. That's the filter, regulator, and lubricator, which essentially preps your fluid, cleaning it up and getting it ready for work. Then you've got the DCV, or directional control valve. This acts like the traffic cop of the whole system, expertly directing exactly where all that pressurized energy needs to go. Adding your pumps to generate the pressure, actuators to do the actual heavy moving, and pressure gauges to keep an eye on the whole operation, and boom, you've got a complete power system. Moving right along to Section 2, Designing System Circuits, Planning the Flow. You know, the manual has a really great way of putting this. The main goal of this phase is to learn how to lay down the circuit. And what that really means is translating those physical parts we just talked about, like the valves, pumps, and actuators, into universal symbols. It's basically a visual language that lets any trained engineer or technician, literally anywhere in the world, look at a schematic and instantly understand exactly how that power is supposed to flow. If you look at this, you'll notice how the whole progression of circuit design happens in three very distinct phases. First, you have to master the symbols, figuring out how to describe components on paper. Next up is generation, where you create the actual schematic using CAD or computer-aided design. But hold on, you don't build it just yet. The absolute crucial final phase is simulation. By using advanced tools like computational fluid dynamics, technicians actually simulate the fluid flowing through virtual pipes. This ensures total safety and efficiency before a single piece of real metal is ever even cut. And that brings us to Section 3, Building and Testing Systems. Theory meets reality. So, supplying and commissioning one of these pneumatic or hydraulic systems is a very strict step-by-step procedure. You really can't just skip ahead. Step 1, you have to interpret the schematic you just designed. Step 2, you get hands-on and physically build the system, carefully connecting every single valve and gauge. Step 3, you safely run your tests by introducing the pressurized liquid or gas into the system. And finally, step 4, which honestly might be the most critical part of a technician's entire job, you hunt down the inevitable faults.
Because you see, describing and then actually executing these pneumatic and hydraulic troubleshooting procedures is what truly separates a total novice from a level 5 certified expert. I mean, think about it. If a system suddenly loses pressure or one of those directional control valves sticks open, the entire manufacturing line just grinds to a halt. A trained technician has to use their deep foundational understanding of fluid mechanics, viscosity, and circuit logic to diagnose and fix this invisible problem hidden deep inside those thick steel pipes. It really is the ultimate test of their mastery.
And maintaining that high level of mastery, well, that requires some absolutely incredible educational standards. Frameworks like the TVET Quality Management Project, or TQMM, provide the kind of highly structured training that's so desperately needed here. It's these rigorous modules that ensure the technicians behind our modern infrastructure, the very people building and repairing the machines that build our world, know exactly what they're doing every single time. I really hope this explainer has kind of transformed how you look at industrial automation. We've traveled from the basic principles of fluid mechanics through the whole digital simulation of complex circuits, all the way to the gritty physical troubleshooting of these incredible systems. So the next time you see heavy manufacturing equipment in action, or you're just driving past a construction site, I want to leave you with this thought. Ask yourself, which invisible fluid is quietly doing all the heavy lifting right there in front of you? Thanks so much for joining me on this deep dive, and as always, keep learning.